Okay, here are some solutions to the first derivatives quiz. Number 1. Well, we have a composition of functions here, one function inside of another one, and also a fraction. So we're going to have to use the chain rule and the quotient rule in some order. And to decide what to use first, what you want to do is imagine plugging in a value for x and then simplifying this expression. And you want to think, what's the last thing you would do? Okay. And the last thing you would do is to take the tangent of whatever this fraction was. And so that means we have to use the chain rule first here. Okay. So the derivative is going to be well, I sort of circle the inside function here if you like, and then take the derivative of the outside. Derivative of tangent is secant squared. And then you just keep whatever was in the circle. And then you, excuse me, you want to multiply that by the derivative of the inside function. So let me not do that quite yet, but I'll just write the inside function and put a box around it to remind myself to take the derivative. Okay. And now we can go ahead and take that derivative. So I'll copy this first part. Okay, this is the derivative of a fraction, so we're going to use the quotient rule, low d high minus high d low over low squared. And okay, put a big parenthesis here. We want to multiply this first part by everything that we write hereafter. And okay, low d high is going to be 3x plus 8. And then the derivative of 2 is just 0. All right. Minus high d low. Derivative of the denominator is just 3. All over low squared. Okay, good. And we should try to simplify this stuff a little bit. So let me do that over here. Secant squared of 2 over 3x plus 8. And what do we have here? Just negative 6 over 3x plus 8 squared. Okay, great. Now there's actually one other way we could have done this derivative of this fraction right here. So maybe I'll show you that as well. The thing is, since the numerator here is just a constant, you see that the quotient rule, sort of part of it, didn't even matter. And so what you can do is actually view this fraction in the box here as just 2 times the quantity 3x plus 8 to the power negative 1, and then actually use the chain rule again. Okay. So, all right. So we're copying our secant squared from up here. And then, okay, multiplying by the derivative of this function. And so that 2 is a constant multiple, so you just pull it out of the derivative. And then, all right, we have the derivative of this to the negative 1. We use the chain rule, circle the inside function. Derivative of that circle to the negative 1 is negative 1 times the inside function to the negative 2. And then we have to multiply by the derivative of the inside function. The derivative of 3x plus 8 is 3. Okay? So, if you simplify that, hopefully we get the same thing as before. All right, we have negative 2 times 3 is negative 6. And then this to the negative 2 is the same thing as it's 1 over 3x plus 8 squared. So we do indeed get the same thing. All right, so yeah, either of these two options for taking the derivative of this fraction are fine. Now, if you had something more complicated than 2 on top, like something involving x's, then you might as well just do the quotient rule. Okay. All right, let's try the next one. We have, well, a composition here, so there's going to be a chain rule at some point, and then there's also a product. And the last thing you would do if you were computing this is to multiply this first factored by the cosine x. Okay, so that means we need to do the product rule first when we take the derivative. So, okay, again, I'm going to kind of write out all the steps. If you're feeling comfortable with these already, you don't need to do this. Okay, with these boxes and all. So I'm going to just copy this thing twice with a plus sign in between. Okay, and then for the product rule, I need to, in the first term here, take the derivative of the first factor. And in the second term, take the derivative of the second factor. Okay, so it's sort of putting boxes around the outside two factors. That's the product rule. And now I'm going to compute the derivatives of these things in boxes. For the first one here, I need to use the chain rule. So it's going to be circle the inside function x to the fifth minus 3. Then I have that circle to the fourth power, so the derivative of that is 4 times circle to the third power times the derivative of the inside, which is 5x to the fourth, and the negative 3 has a derivative of 0, so I don't have to write that. Okay, so that's the derivative of the thing in the box, and then I have the cosine x here as well, and I'm going to add on x to the fifth minus 3 to the fourth power times the derivative of cosine x, which is negative sine x. So that's my derivative, and I should probably think about if I can simplify it a bit. Any common factors? Maybe just x minus fifth to the third, right? Because there's at least 3 copies of that over here too, and I don't see anything else that they have in common. So let's just factor that out. 3 copies of that factor, and then okay, what's left over? In the first term, I have 4 times 5 is 20x to the fourth times cosine x. And in this one here, oops, I actually have a minus sign there. So let me get rid of my plus sign and say minus from this minus sign. And then I factored out 3 copies of this factor, so I have 1 left. And I have a sine x, right? Okay, so x to the fifth minus 3 to the first power times sine x. All right, and that's about as good as I can do. Okay, we're halfway there. Number 3, we have a quotient, and in the denominator we have a composition again. Okay, and if you're going to evaluate this, you would figure out what the denominator is, and then the last thing you do is to divide. And so that means we have to use the quotient rule first when we take the derivative. Okay, and so low d high minus high d low over low squared. All right, so there's the low, and d high, derivative of the numerator is just 1, minus high d low, right? So maybe I will put that off for a moment and just say we need to calculate the derivative of the denominator right here. And then all of that is supposed to be divided by low squared. And using our sort of shorthand, we can say that sine squared of square root of x, right? Remember, what this really means is sine of square root of x squared. Okay, so you can't cancel the square root with the square, because the square root's on the inside of the sign, the square's on the outside of the sign. So the sign is sort of in between them. It won't let them cancel out. All right, well, we're not too far away now. So we have sine of root x minus x. Okay, and then for this one, it is, oh, that's interesting. See if I can fix that. Yeah, this thing inside the box can be thought of as sine of x to the 1/2, right? So the inside function is x to the 1/2. And so with my chain rule, I get derivative of the outside function, which is cosine of x to the 1/2, then times the derivative of the inside function, which is 1/2 x to the negative 1/2. And all of that is still over sine squared of root x. All right, and now let's see if we can simplify a little bit. Sine of root x and minus 1/2, and I also have x times x to the negative 1/2. And this is like x to the 1, right? And when you multiply powers of x, you add the exponents. 1 plus negative 1/2 is positive 1/2. So that becomes x to the 1/2, or square root of x. All right, so if I take 1/2 times square root of x, I can write that as square root of x over 2. And then still have a cosine of square root of x right there. And I'll put the whole thing over sine squared of root x. Okay, and there's other ways to write that, but that's fine. All right, last but not least, we got a cosecant squared in here. So, okay, we should try and rewrite this thing before we take its derivative. Cosecant squared means compute the cosecant, and then, square the whole thing in the end. Okay. So we have a 5x cubed function inside of a cosecant inside of a square. So we're composing three functions here. We're going to have to use the chain rule twice. All right. So begin by circling everything except the sort of outside layer of your onion here, the outside function, and apply the chain rule in this situation. So the derivative of circle squared is just 2 times circle. So 2 times cosecant of 5x cubed. And now we have to multiply by the derivative of the circle. Okay, and that's still a composition, so we still need to, let me just sort of write what we got. So we have to take the derivative of cosecant 5x cubed. Okay, so that's what we got from the first application of the chain rule. Now let's try and finish it off. Copy this first part. Okay, so now we circle the inside function again, and we have to take the derivative of the outside. Let's see if I remember what the derivative of cosecant is. Well, secant is secant tangent, so cosecant must be negative cosecant cotangent, which means negative cosecant of your circle times cotangent of your circle, right? Okay. And so that's the derivative of the outside, evaluated on the inside. And now I need to multiply by the derivative of the expression in the circle, which is, let's see, 3 times 5 is 15, x squared. Okay, so this derivative by the chain rule gives us this. And we're done taking derivatives, so we just need to see if we can simplify it all. And, well, everything's just multiplied together, right? So can't do a whole lot, although we could, okay, we have a 2 and a 15, so it's supposed to be equals, so we can write that as 30, and maybe bring the x squared out front. And then maybe take this minus sign in front of everything. And then I have the trig stuff left. I actually have two factors of cosecant of 5x cubed, so I can write that as cosecant squared of 5x cubed. That's interesting. That was our original function, wasn't it? And then I have a cotangent remaining. Cotangent of 5x cubed. And I think that's the same thing we had in the previous line. So we'll call that our answer.